This is lecture 2 for Challenge Math 2000. Our main goal here is to start arming ourselves with theorems that are going to allow us to find the limits of sequences. And so the first theorem that we'll discuss is basically telling us that most of the arithmetic that we would like to be able to do with sequences, we in fact can do. So if we have two sequences, an and bn, and two numbers, a and b, such that an converges to a and bn converges to b, then what can we say about the limits of sequences that we get by combining these two sequences? The first one is what if we just take the sum, so the sequence whose terms are the sum of the an term and the bn term. That gives us a new sequence, and that sequence, well, we would like for it to converge to a plus b, and that's exactly what happens. And you can do the same thing if it's a minus b. The next part involves multiplication by a constant. And so it basically says that if you have, if you multiply every term of the sequence by a constant, then the new sequence that you get is going to converge to that constant times the limit of the original sequence. Next come multiplication and division. First, if you multiply an and bn together, then that sequence is going to converge to a times b. Finally, as long as we have that b is not 0, and you can say that an divided by bn converges to a over b. Now let's see what we can prove just armed with this theorem and theorem 4 that we discussed last time. So let's compute the limits of these two examples. So we'll start with number 1. We have 3n squared plus 5 over 7 minus 8n squared. And we can rewrite this nth term by dividing everywhere by n squared. And now we know that 7 over n squared, well, the denominator is going to go to infinity, so this term goes to 0, and similarly 5 over n squared goes to 0. So by the rules that we saw on the previous slide, this sequence is going to converge to 3 plus 0 divided by 0 minus 8, so negative 3/8. Now for number 2, we're going to compare this sequence to the function that we get when we put an x in place of the n, namely 2 times natural log of x over 9x squared. And because this function defines this sequence, if we can find the limit of the function, that will also be the limit of the sequence. Now, as x goes to infinity, this numerator, 9x squared, goes to infinity. Sorry, the denominator goes to infinity, and the numerator, 2 natural log of x, also goes to infinity. So this means that the limit of this function is infinity over infinity. So we can use L'Hopital's rule. The derivative of 2 natural log of x is 2 over x. And the derivative of 9x squared is 18x. Therefore, applying the theorem and L'Hopital's rule, we see that the limit of our sequence is the limit of the function, which by L'Hopital's rule is the limit of the quotient of the derivatives, but of course this x goes to the denominator, so really we have the limit as x goes to infinity of 1 over 9x squared, which is 0. The next important tool to study convergence of sequences is called the sandwich theorem. So if we have 3 sequences, and an, bn, and cn, and not necessarily right at the beginning, but after some point, we have that one of them is always between the other two. And suppose further that the two outside sequences, an and cn, both converge to the same place, to the same limit. So let's look at a heuristic picture of what we mean. So if we have one sequence that is sort of moving around but converging eventually to some value, maybe that's our a sub n, and we have another sequence, c sub n in green, which is around and which eventually converges to the same place as an. And we have a third sequence, bn, which at the beginning doesn't necessarily need to be between the two, but then after some point it does lie between them. Then that bn, since it's sandwiched between the other two, so it basically has to have the same limit in the end. So that's the heuristic picture. And an important special case of this is when we consider one of these sequences to be maybe the constant sequence just equal to 0. By the way, I just noticed that I've sort of reversed the roles of an and cn from what I've written up here, where cn is the one which is bigger. So hopefully that's not too confusing. So let's see what we can do with the sandwich theorem. Here's an example that we can use the sandwich theorem on. So the sequence is sine of n divided by n squared. And we want to use something that we know about the range of the sine function. So let's just recall what the graph of sine looks like. It starts at 0 at the origin, and then it has this sort of nice oscillating pattern that goes on in both directions forever. And it oscillates between 1 and negative 1. So what that means is that the numerator of our sequence is always going to be a number that's sitting in here somewhere between negative 1 and 1. So we can write that as an inequality. This is true for all n. Okay, so then how does that let us use the sandwich theorem? Well, we can do the following thing. So if bn is negative 1 over n squared and cn is 1 over n squared, then we know that both of these sequences go to 0. Their limit is 0, and sequence an is always between them. Therefore, by the sandwich theorem, we can conclude that an goes to 0. Finally, let's talk about bounded monotonic sequences. Monotonic sequences are either non-increasing or non-decreasing, or both. So let's look at non-increasing. So if you have a sequence that is never moving up, so we would say formally that an plus 1 is less than or equal to an. So that's non-increasing. And then non-decreasing is sort of the opposite idea, namely that the n plus first term is always greater than or equal to the nth term. So maybe something like this. So if a sequence is either non-increasing or non-decreasing, it's called monotonic. What about if a sequence is both non-increasing and non-decreasing? Then you would have that an is less than or equal to an plus 1, because it's non-decreasing, but because it's not also non-increasing, you'd have the an plus 1 is less than or equal to an. And that means that the two have to be equal. And that means that your sequence is actually just a constant sequence. Now let's discuss the notion of boundedness. First of all, if you have a sequence and you have some number that is less than or equal to any term in your sequence, like so, then this sequence is bounded from below. Sequences can also be bounded from above. And if it's bounded from above and below, then it's just called bounded. So if it's bounded from above and below, then it might try to move around, but it has to stay in this area of finite thickness between the two bounds. So this condition by itself of being bounded doesn't guarantee anything about convergence, because the sequence could just kind of bounce back and forth. So an example is, again, -1 to the n. But what about when we put the two conditions together, boundedness and monotonicity? Then let's just say, for the sake of example, that we have one which is monotone, non-increasing, so decreasing, and also bounded. So then we have something which is getting smaller, but then it has nowhere to go. So, oops. So a sequence that looks like this one converges, and this is an example of Theorem 6. So Theorem 6 says that any sequence that's both monotone and bounded must converge. And before we finish this lecture, I just want to call your attention to one other theorem that is in the textbook and that you need to look at as part of your homework. So please look at the examples of some convergent sequences that are mentioned in Theorem 5 on page 556, as well as doing the online homework. Next time we will begin talking about infinite series. So see you then.